for internal loads number 6. Here is how I know what those dimensions are.
I figured it was a meter from your...
Yeah, that's from the solutions. Just look at what I used in the solutions. I guess I never updated.
You just gave us like the row vector, so I converted it back to like the hypotenuse.
Okay.
Yeah.
Yeah, let's.
And then I figured out the angle from that.
Yeah. So I'll tell you right now.
The pulley itself that has some radius.
Okay, internal loads. So here are the problems, and it's this one. And the solutions for internal loads. So
using like negative 0.086 and 0.492, you can figure out the...
Yeah. Yeah, so I guess, okay, the about point I chose was at the middle. Yeah, it's each one is 1 meter long. And that, what?
Each one is actually
the whole length of the thing is 1 meter. And the angle is, each of those angles is 80 degrees.
And then the pulley thickness.
And the pulley thickness, I think, will not matter because the 2 radii will cancel. But let's go through the beginning of that. Let's go through just the external loads of that, or at least get started. Okay. $300 newtons. Okay, so it's like that. The lengths are each 1 meter. And this angle is 80 degrees, and this angle is 80 degrees. And there's no weights or anything. I don't think I'm missing anything, am I? I think that's it. Okay, so let's call this one 1 and this one 2. So a free body diagram of body 1. We have the force, let's see, let's call this A, B, C. So down here we have the force RC. Here we have the force F12. And here, let's include the pulley in this system. I'm not going to redraw this. I'm just going to, so I'm going to like include the pulley and the cable that goes around the left side of the pulley. Okay. So then you can see that the forces coming out of here are 300, 300. So RC, I will choose that as the about point. So row vector is 0. Force is RCX, RCY. Moment is 0. Then we got F12. The row vector is negative 0.09, positive 0.492. Force vector is F12x, F12y. Cross product is negative 0.09 F12. Let me keep another digit on this one of 0.087. Okay, so negative 0.087 F12y minus 0.492 F12x. And now these are horizontal forces. I'm going to start with the lower one. So where's the location for that? That's a horizontal force. So all we need is the height of that row vector. And so if we go to so I'm going to assume that the pin, the middle of that pulley is at the top of that member. Does that seem reasonable? I guess really you should say the top maybe is at that member. Okay, so I'm going to go, for the lower one, I'm going to subtract 2 times the radius of the pulley from the height. Okay, I'm going to get the height of the whole thing. And then I'm going to subtract the diameter of that pulley to give us the height where that lower 300 is coming out.
So we're saying the top of the pulley is flush with the top of the member?
Yes, so that's what it would take for that cable to be horizontal. And that cable looks horizontal.
The cable's going in, okay, I see. It's not going to the top of the pulley.
Yeah, well, there's okay, and the radius of the pulley I'm talking about is the radius of the inside, not the bracket on the outside or whatever, you know, so it's very small.
It's in a channel, okay.
Yeah.
How do we know the radius of the pulley?
We're going to put it in as R. And what we're going to see, I think, is that it just cancels out.
Yeah.
you have two of them. But let's see. And if it doesn't cancel out, then we're going to be discouraged for a little while, and then we're going to think about what to do next. Okay, so so the row vector, well, it's going to be, I'm not even going to worry about the horizontal component of the row vector. So I'm just going to call that 0. The y is going to be 0.985 minus 2r. And the force is negative 300, 0.
Why would we care about that?
Because the line of action of this force is this. So yeah, you can put it anywhere. Ah! Okay, so 0.985 times 300. So we have positive 295.5. And then minus 600R.
I missed why it's negative 300.
Because the row vector, the vertical component of this row vector is the vertical vector, from the about point up to where that force is applied. The up to the red line is 0.985, and then we're going down less than that by an amount of 2 times the radius. We're trying to figure out the height to this, right?
Right.
And the height to the top dotted line is 0.985.
In the force
no,
column.
he's talking about the force.
Why is the force negative?
It's pointing to the right.
That is correct. You are right about that. But wrong about the other thing. Okay, so this is minus, this is plus. Okay, and I don't really see anything that's going to cancel about that R.
That's what I was saying. It's a fun friend.
Yeah,
I mean,
this is 0.985. This is 300, 0. And so that is negative 295.5. And so these equations, okay, well, you get the Newton's second law equations there. And then the moment equation, your equation 3 is going to be negative 0.492 F12x minus 0.087 F12y is equal to 295 times 2. So that's 591 minus 600R.
I think if you put it so that the center point of the pulley is on the end of the member,
Yeah,
then it will cancel.
yeah, that's true.
Because those two vectors are like.
Yeah, that's what I was expecting it to do. So I guess those are the two options where you could use to solve this. I wonder if I chose a radius for that pulley in my solution.
Because they have different moments. In the expression.
Uh,
Up a little. And the radius is like 0.1. If we look at the P vector.
oh, yeah, I don't talk about it that way anymore. But P is the coordinates of the point where the force is applied. A is the coordinates of the about point. And if you figure those out, then you can just subtract and it'll give you the row vector. So that's how I used to write out this table, but now I just skip all that. Okay, 0.392 and 0.492, right? So the diameter of that pulley, it looks like I have as 0.1. So the radius is 0.05. So I just chose a number for that in my solution. Ideally, the person who wrote the problem would have given you those numbers, but
Would it even, couldn't you just look at it as two forces? Is they're both the same distance from the center, and they're both acting in the same direction, so one they just all act like 600 and on to the 10? 600 newtons, one they just,
that is what I expected it to do.
could we just assume that, because we know how that can work?
That's assuming that that's the same as assuming that the radius is, well, so you have this one moment that's, it appears that you can assume that if the I think you can't assume that because you don't know where the center of that pulley is. If we had done it like we know where the center of that pulley is, if I had said, okay, the center of the pulley is at the top of that member, then it would work out like you're saying.
Okay.
Instead, I said, my first look at it, I was like, it looks to me like the top of the pulley is at the top of that member. So we know where the top is, but we don't know where the center is. That's why it's a problem. So without having that information, I would say like, okay, we're gonna assume that the top of that pulley is at the center of that pulley is at the top of the member, and then you can calculate everything.
Yeah.
I mean, when I wrote this problem, I wasn't expecting you to think all this stuff through. I just forgot to put down dimensions, but so I need to put down dimensions. But those are sort of your two options. I mean, you either make up dimensions or you assume that the center of that pulley is at the top of the member.
You always just carry a variable all the way through, right?
You could do that, yep, and then your answer would have R in it. But yeah, it's interesting that, I mean, we've seen ones before with pulleys like this, and they were set up like we knew where the center of the pulley was, and so R didn't end up mattering.
Mhm.
Here, we know where the top of the pulley is, but not the center, the way I was thinking of it. And so with that small difference, the size of the pulley actually does come into the problem.
Mhm.
So I have a question about pulleys.
Mhm.
So there's one 300 Newton force.
Yeah.
But when you draw the free body diagrams, you have three 300 Newton forces.
Yeah, that's right. That's right.
So how does that like work? How do you have extra force in your free body diagram?
Yeah, remember doing those problems with the block and tackle in the particle statics? It's okay, so wait, let me first let me just write something down about this one. Okay, so either choose a pulley radius or put the center, the pin of the pulley at the top. Shruggy guy emoji. Ooh, he has big shoulders. Okay, what do you want from me? Okay, so, well, I mean, how it works, I guess, like really the best answer to how it works is drawing the free body diagrams. I mean, if you can choose a thing to, if you can choose a set of bodies or parts of bodies or whatever, that you can put an entire closed outline around, and then you can give all the external forces for that. I mean, that's how it works, you know, better than I can say in words or whatever. But with the block and tackle system, remember we had something like this. And we had a cable that went under this hanging pulley and then up to this one. And then we were calculating the force that's required to keep this in static equilibrium.
The pulleys are frictionless, right?
We did assume that the pulleys are frictionless. Yes, and we also assumed that the pulleys had no mass. I suppose that's easy to put into the equation. The mass, just include the mass of the pulley here. In dynamics, by the way, we'll talk about how to deal with pulley mass and cable mass, because we're also assuming that this cable is massless. Okay, so here's what I'm going to take as my free body.
So it takes like 4 years of physics to finally get mass on the cable.
Yeah, exactly. But that makes it more satisfying when you get to it, you know. Okay, so here's my free body. So notice that I'm including, not only am I including everything that's hanging from the cable, you know, but I'm also including a little bit of the cable that goes underneath this pulley. But now, so now here's the free body. So we're including some cable in our free body and we're not including some cable. So what's the force that the not included cable applies to the included cable? Well, that's easy, you know, that's just a cable tension. And since this is the same massless cable and frictionless pulley, these two forces are the same. And so now you have 981 here. And you can see from that, if this is in static equilibrium, each one of those cables takes half of that weight. And so you can support a force of 981, a weight of 981, by only pulling 490.5. That's how it works. I mean, what do you want from me?
Is
You
this
know?
because the ceiling is doing?
Yeah, that's right. The ceiling is taking some force, yeah. Also, this feels like a brain teaser. You know what I mean? Like find where I tricked you or whatever. You know what I mean? It does feel like that. I agree that it feels like that. But we could go into the mechanics lab and take out a pulley and take out a string and take out a weight and hook it up first like
single pulley versus two.
Yep, first hook it up like this. And see how hard you have to pull to hold it up. And then hook it up like this and see how hard you have to pull. And I'll be damned. Like, there's no denying that you're holding half of that weight, you know?
So does the cable like move? Do you have to move it further?
Yeah.
Yeah.
Yes, because you can't get any free energy, right? There's conservation of energy says you can't, you have to apply an amount of work to this that's equal to lift the same thing. So yes, not if you're just holding it, but if you're gonna lift this weight an inch, you have to, so think of like if you're raising this 100 kilogram object 1 inch, you have to raise each of the two, you have to shorten each of the two sides of the cable going around that pulley an inch. And that means that you're actually pulling a distance of 2 inches.
Okay, that helps a little bit. Actually.
Yeah, okay.
It's
That's
gearing
like-
down
that's a
to
ratio.
position.
What?
That's like the kind of gear ratio of.
Yeah,
Yeah.
yeah, that's right. It is a gear ratio. You're right. I haven't thought of it that way, but that's what it is. Yep, exactly.
You can spin twice as fast on this stuff.
Yes,
That's
right.
why
It's a
when you
gear
use-
ratio.
Like when you go rock crawling with Jeeps in the Rocky Mountains, you always bring 2 or 3 pulleys and make sure your winch is long enough.
Really?
Yeah, I mean,
Huh.
that's what we do. You get a pulley
For in case you have to get your car out, you mean?
back to your vehicle
Yeah.
and to the tree again.
Yeah.
And then because
Right.
to pull yourself out or with whoever.
Yeah. I mean, I know that like in shipyards and stuff, these block and tackle systems are things that you just have like lying around with big hooks on each sides. And yeah, it's a thing.
It is.
You can do that as many times as you want, right?
Yep.
Like adding-
Yes, except there are energy losses due to friction each time you do it. So at some point you reach a limit of where it's helping you anymore,
But not in our
in practical speaking. But in our world,
it's
it works
limited.
unlimited, exactly.
So it's like the extra amount you have to pull it is for each pulley you add, you just add 1. So you have to pull it like 3 times or 4 times.
So you always need, in the system, you always have to add, it has to go, in multiples of 2, because you need, for every hanging pulley, you need another pulley that's attached to the ceiling. And so every time you add 2 of those pulleys, you're adding 2 new things to take the force. So like if you, and a block and tackle system, they don't do it like this because it takes up a lot of space, but this is the principle of what they're doing. So there. This force, your free body diagram. Your free body is this. And so now you can see that the forces you have are 981 going down, and then you have 4 of these T forces. And so adding 2 more pulleys means you divide by 4. And then if you add 2 more pulleys, you divide by 6, and then 8.
Then you have to pull 4 times as well.
Right, yep.
So the distance you have to pull is 2 to the n over 2.
The work has to stay the same. So, so as that force goes, so as you divide the force by 2, you multiply the distance by 2. Remember work? Force times distance. Yeah, so whatever you divide the force by, you have to multiply the distance by. Okay, let's start doing, I want to do an example problem sort of like this. We haven't done one like this. We did one where we had weights on the members, and so we had distributed loads that we had to use the rotation matrices for. But the problems that you have to do with rotation matrices don't have weights. So I'm going to just do one of these simpler ones. Okay. Actually, just so I can fit it in, I'm just going to do it like this. I am going to so let's say we have a cantilever beam at an angle like that. Let's say this angle is 50 degrees. And we're going to have sorry, I'm going to switch this to the other direction. Okay, so this angle is 50 degrees. And then I'm going to have, at the midpoint, a force straight up of 500 newtons. And then at the end, I'm going to have a force straight down of 500 newtons. And we're going to neglect the mass, and this angle is 50 degrees. And we want to calculate the internal loads. All right. We're going to have to do some funky trigonometry here. So how are we going to come up with these row vectors, you know, like along this beam? Here's my coordinate system. Oh, and I need to give a length. Let's say the length is 1 meter of the whole thing.
What's the rate?
There's no pulley. Okay, so what I'm going to do is I'm just going to go around using the relationships that I'm given. I'm given that it's 50 degrees from the horizontal to that wall. So the first vector I'm going to draw is going to be 50 degrees from the horizontal. Okay, so we know this angle is 50. And then the next angle we know is 90 degrees from the wall. So I'm going to draw a vector like this. Okay? And that is the vector that goes along this member. Are you with me on that? Okay, so I'm going to go, so now to come up with my angle for cosine and sine, I'm going to go positive 50. And then I'm going to go, negative 90 because I went counterclockwise and then clockwise. So theta is equal to plus 50 minus 90, so negative 40. Okay, so free body diagram. We have this reaction force R and this reaction couple MR. And then a 500 Newton force there, and a 500 Newton force there. And I'm going to choose this as my about point. So for the force R, row vector is 0. Cross product is 0. For the couple, none of this stuff matters, and the moment is MR.
Do we say 500 for both forces?
Yep. And then the 500 at the midpoint. The whole thing has a length of 1, so this is going to be 500. No, I'm sorry. This is going to be 0.5 times cosine and sine of negative 40. So the row vector is 0.383 negative 0.321. And the force is 0, 500. And we get a cross product of 191.5. And then the 500 Newton force at the end. That is a row vector of 0.766, negative 0.643. Cross product is 0, negative 500. And so you get a cross product of negative 383. So Newton's second law says Rx Ry plus 0, 500 plus 0, negative 500 is equal to 0. And so R is just equal to 0. Okay. Well, I didn't mean to do that, but and then the couple is, so we got MR is equal to negative 191 plus 383. So this is equal to plus 191.5. Okay, so we have this beam like this. We have a counterclockwise couple of 191.5, an upward force of 500 here, and a downward force of 500 here. We don't have to do anything, and this is in a coordinate system like this, right? We want to re-express everything in a coordinate system with the x-axis along the beam. The way that probably would occur to everybody is to do it like this, where my thumb is the x-axis. But notice you always have two choices. You know, you could do it like this, or you could do it, if you're flexible, like this, you know. Okay? In this one, 0 out of 1,000 people would choose this. But in other ones, like in that homework problem with the X and the pulley and stuff, on the one that's facing this way. You know, some people would do it like that and some people would do it like that. And it's either way, it's the same. The functions will look different. But if you plug an X value into the function to see the internal load at a single point, they agree with each other. Okay, so it doesn't matter which side you choose, but I'm going to do it like this. And we've already figured out that that takes a theta of negative 40 degrees.
That's 40 degrees in the clockwise direction.
Correct. Okay, so our rotation matrix is cosine of negative 40, sine of negative 40, negative sine of negative 40, cosine of negative 40. And that is 0.766, negative 0.643, positive 0.643, positive 0.766. Okay, I want to tell you the easiest pitfall, easiest mistake to make. So remind yourself every time not to do this. We're used to looking at this body horizontally for internal loads, right? So it's really easy to think that what you're doing is rotating this body to make it horizontal. But to rotate this body and make it horizontal would take an angle of positive 40 degrees, right? That's not what we're doing. We're going from a starting coordinate system to an ending coordinate system.
We're rotating ourselves.
Yes, we're rotating ourselves. Or like Matt said, we're rotating the camera that we're looking through, you know. I think that's all, a camera or a video camera is always a good way to think about what a coordinate system is, you know. If you think about rotating the body, all your angles are backwards, okay? All right, so now we have this, and now we have to figure out how to treat these loads. The couple, do we rotate that? Correct. No, we do not rotate the couple because remember what a couple is, what a moment, any moment is.
Out of point, spinning around.
Yeah, I mean, it is a vector. And when we're in 2D, we sort of obscure the fact that it's a vector, but it's a Z vector component, okay? And so we're not changing the orientation of Z. Okay, so this is still perfectly fine, but we do have to treat these two forces. So we'll go Q times 0, 500. And that is
When you're doing this in your calculator, are you just putting the investments in the meaning and then multiplying with the other?
yeah. I am right now entering a matrix.
Because I was trying to find out if I could like program and one of those.
Yeah, that's a good idea. In D form, we will do that. And then I usually store it in a variable. So what I mean, you all have different calculators is the problem. I think if you look at that PDF, well, it's broken up into a bunch of PDFs, but if you go to D2L and look at the textbook thing that's posted there, I think there are appendices that tell you how to enter these into different kinds of calculators. I'm pretty sure that's the case.
Oh, okay. Because when I had programmed I think it was
Here, let's just finish this and then I'll show you where the, okay, so you get a vector like this. That's the one at the midpoint. And if you do that with the other vector, you just get the opposite components. So 321.39, negative 383.02. And so now that we've reoriented the coordinate system, we can think of it as horizontal. And we have a couple of 191.5, a force in the middle of negative 321.39, 383.02, and then at the right end, positive 321.39, negative 383.02. And now that's a really easy internal loads calculation. Any questions about that? Okay. Let me show you where in D2L you can find this stuff. Did I tell you guys that somebody once, so in D-Form you'll have to enter a bunch of programs in your calculator. We'll make sure you have that all entered right and stuff. But I had a student in D-Form once who bought a calculator from Pan America. Did I tell you that?
Yeah,
Oh, okay. And all the programs were in it. Like somebody got done with my class and was like, this is stupid. I'm never doing this again. Okay, go to content, statics text, and then
Oh, the A one. Okay.
multiplying matrices, solving systems of equations, rotation matrices.
Oh, cool.
Yeah. And so,
I didn't realize this was the other thing. So I definitely just looked up how to do on YouTube for the cross product.
oh yeah. So look how cool that is. Like all the different calculators. You should use it because it took me a long freaking time to do this. Okay, that's all.
Wolfram Alpha is so convenient.
What?
Wolfram Alpha is so convenient.
I know.
It saved me a couple of work.
Yes. The problem with Wolfram Alpha is you can't use it in a text.
Yeah.
Test, I mean, an exam.
One of our teachers did let us.
Oh, yeah?
Ours was take home tests, and he's like, go ahead and use Wolfram Alpha.
Well, yeah, take-home test. I mean,
No, was
Oh,
in class.
yeah. That's just pretty trusting. Good for him. More power to him.
The problem
I
with
think
Wolfram is
my thought process, my guess is his thought process was if you made it to Calc 4 and like you're figuring out at least how to get an answer for it, like no matter what method you use,
Yeah.
you're getting an answer.
I hear that. Yeah.
you can put in matrices
That's how
bigger than
for-
like 5 by 5.
No,
That's what I was gonna say. I've never
I
used
used
Wolfram.
In Wolfram Alpha?
Yeah, because
Like teacher for
I
Calc
we
4
had
is
to
very
do stuff
specific.
that was like 10 by 11 or something
That's
like that.
Son with
Yeah.
It just
The matrices aren't big enough in Wolfram.
Hold on a sec. I have to look at something real quick. Solving systems of equations.
We had to do analysis.
So we got all these. My calculator's like filthy dirty in my pictures.
Jeez, don't you go wash them?
Every Sunday morning, I wash my calculators in the yard. Okay, hold on. But I want to look at Wolfram Alpha to see if Wolfram Alpha, mathematics, math input. You're right. I didn't do a big one. Maybe you can't. I don't know. That's funny. It's not very useful to use reduced row echelon form if you can only do 5 by 6 matrices.
Yeah, for
Yeah.
Calc 4, the base we did is 7 by 8.
Hmm.
We had to do like analysis. Of,
Yeah.
like, the flow after that.
But here we did a 15 by 15, right? For one of the problems.
Is this matrix in the subspace of this
Put the
matrix?
notes.
Yeah.
That shows.
Did you put it to the part where you calculated the moment?
Oh yeah, we got to go to the other room. The calculated the moment,
I
the
would
external
do
loads.
conditions where added into the-
Okay.
So yeah, I mean, I just added those two.
But isn't
Sure.
there, is there an easier way to just all these?
There is a way to do